In this code, I am building a complete natural language processing and machine learning pipeline using Shakespeare's Macbeth text from the NLTK Gutenberg corpus. The main goal of this program is to compare the effect of different text pre-processing techniques, raw text, clean text, and stemmed text on word embeddings and classification performance. First, I install and import the Gensim library. Gensim is a powerful library used to train Word2Vec models. Word2Vec is an algorithm that converts words into numeric vectors so that machines can understand relationships between words based on context. After successfully importing Gensim, I import the NLTK library, which stands for Natural Language Toolkit. I then download several important resources, including Punkt for tokenization, stopwords to remove common words, and the Gutenberg dataset, which contains classic literary texts, including Shakespeare's Macbeth. Using the Gutenberg corpus, I extract the full text of the play Macbeth and store it in a variable called Macbeth_text. I also initialize a list of English stopwords and a Porter stemmer, which is used to convert words into their root form. Next, I create 3 different versions of tokens from the text. The first version is called tokens_raw. This simply tokenizes the Macbeth text into individual words using NLTK's word tokenizer without any cleaning. The second version is called tokens_clean. Here, I convert all words to lowercase, remove any punctuation or numbers, and remove stopwords. This gives me a clean version of the text without unnecessary words. The third version is called tokens_stemmed. This version is similar to the clean tokens, but additionally applies stemming. Stemming reduces words to their root form. For example, running becomes run and killed becomes kill. I print samples from all 3 versions so that I can visually compare the difference between raw, clean, and stemmed text. After this, I prepare to find most similar words for a given word. I choose the word Macbeth as the query word. I also define a function called safe_most_similar. This function first checks whether the word exists in the Word2Vec model's vocabulary. If it does, it returns the most similar words. If not, it returns a message saying that the word is not found in the model. This is important because sometimes, after cleaning and stemming, certain words may be removed, and trying to find them can cause errors. Then I visualize the similarity scores using bar graphs. I create a function called plot_similarity, which takes similar words and their scores and displays them using matplotlib. I use this function for both the clean and stemmed models to see how well each one understands relationships between words. Next, I train 3 separate Word2Vec models. One model is trained on the raw tokens, one on the clean tokens, and one on the stemmed tokens. All 3 models use a vector size of 100, a window size of 5, and a minimum word count of 1. Now I move on to converting sentences into vectors. I split the original Macbeth text into lines and use each meaningful sentence as a data point. I create a function called sentence_to_vec, which converts each sentence into a vector by averaging the vector values of all valid words present in the sentence. Using this function, I generate 3 datasets: x_raw, x_clean, and x_stemmed. Each dataset contains a numeric vector representation of every sentence based on the corresponding Word2Vec model. To create labels for classification, I apply a simple rule. If a sentence contains the word king, it gets label 1. Otherwise, it gets label 0. This makes the problem a binary classification task. Split the data into training and testing sets using an eta-to ratio. I train a logistic regression model on each dataset and calculate 2 important performance metrics: accuracy, which shows the percentage of correct predictions, and ROC/AUC, which measures how well the model separates the 2 classes. All results are stored in a pandas data frame called result. This allows me to clearly see how each pre-processing method performed. To make the comparison easier to understand, I also plot two bar charts, one comparing the accuracy of the three models and one comparing the ROC-UC values of the three models. Next, I apply PCA, which stands for Principal Component Analysis. PCA reduces the high-dimensional vectors down to 2 dimensions so that they can be plotted on a 2D scatter plot. This visualization helps me see the distribution and clustering patterns of raw, clean, and stemmed sentence vectors. Finally, I print a summary that shows all the performance results. I also output which model achieved the highest accuracy and which one achieved the best ROC-UC score. This allows me to clearly identify which pre-processing method, raw text, clean text, or stemmed text, is the most effective for this particular dataset and task. In conclusion, this entire code shows how different text pre-processing techniques affect word embeddings, sentence representations, and machine learning performance in a real-world natural language processing pipeline.